Alright, welcome guys, welcome to our next video in Math 1. We are going over Day 3 Part 2, which variable to solve for. So, let's excited, let's do this. We'll do the same thing we always do. We'll go through the objective in the box, and again, the video is designed for you to pause and try on your own. Use me as a last resource. Let's jump into it. Students will be able to rearrange equations to solve for specified variables in order to write equations that describe situations that involve multiple quantities where the values are not known. So that's just a fancy way of saying, can we rewrite an equation to get a certain variable by itself? Really stuff that we've already been doing, right? So let's go through our first examples here. All right, we got a multi-variable equation here. Faces, vertices, and edges. We got variables that are related somehow. It says that the equation v plus f minus 2 equals e relates the numbers of vertices for v, faces f, and edges in a platonic solid. Platonic solid is a fancy way of saying this shape right here. Write an equation that makes it easier to find the number of vertices in each of the platonic solids described. So, an octahedron, shown here, which has 8 faces. It's telling us what f is equal to. So, pause the video, try it on your own, but f, we are going to make 8. It tells us what f is. So we have v plus, handwriting's getting worse, not better, sorry. Instead of f, we have an 8 minus 2 equals e. So it says, hey, we have 8 faces, plug that bad boy in, but it wants it to make it easier for us to solve for v. So let's rearrange this equation to where we can get v by itself. Alright, so v is right here. I want to get that bad boy by itself. Let's start by combining like terms. Looks like we can combine some like terms first and get a 6. So we got v plus 6 equals e. And guys, how do we get v by itself from here? Well, I got plus 6. We're going to subtract 6. So we get, for our final answer, v equals e minus 6. So there's an equation that solves for v, given that we have 8 faces. Not terrible, right? What about the next one? An icosahedron, I don't know, you have to look that one up, has 30 edges. All right, we know what e is equal to, so I'm going to say v, which we don't know, plus f, which we don't know, minus 2 equals 30. Because it gave us what e is equal to. Now again, we want to make it easy to solve for v, so we're going to get v by itself. Let's see here. I say we just, well, let's add 2 to both sides, maybe. We get v plus f equals 32. And to get v by itself, we got plus f. How about we subtract f from both sides? And we get v equals 32 minus f. So we got the v equation, given that we have 30 edges. Voila. That's essentially what we're doing today. Alright. Very cool. Alright, pause the video, try 2. And on to number 2. A Buckminster, yes, that word, is a polyhedron with 60 vertices. Why don't you Google that on your own? I don't know. It is not a platonic solid, but the numbers of faces, edges, and vertices are related the same way as those in a platonic solid. So, meaning we can use that formula. Write an equation that makes it easier to find the number of faces, which is f, a buckyball has if we know how many edges it has. Alright, well, make sure we can see the equation. It's up top. it says that we have, 60 vertices. So instead of a V, I'm going to put a 60 plus F minus 2 equals E. We want to make it easy to find faces F, so I'm going to solve or get F right here by itself. So it looks like that I have a, looks like I got a 60 and a minus 2 on the same side. So remember, since it's on the same side, I can just go ahead and combine like terms. Don't flip the signs, I don't do anything like that. I can just combine like terms. So 60 minus 2 is 58 plus F equals E. And then lastly, you get F by itself. I can subtract 58 from both sides. So 58 goes bye-bye. And I'm going to subtract 58. They are not like terms, so I am left with simply F equals E minus 58. Nice. Not terrible, right? Alright. We're on a roll. Let's keep it going. Let's change up the color. I'm feeling spicy. Let's go to blue. Blue. Cargo shipping. Alright, sure. It says an automobile manufacturer is preparing a shipment of cars and trucks on a cargo ship that can own or that can carry 21,600 tons. Well, we know that cars weigh 3.6 per ton, or each ton, and the trucks weigh 7.5 tons each. Write an equation. Alright, so I'm going to say cars for C, T for trucks. It says write an equation that represents the weight. Alright. Constraint, we know what constraint means, of the shipment. Let C be the number of cars and T be the number of trucks. Alright, well I know that for cars it's 3.6 tons for every car, C. And I know that if I take 7.5 tons for every truck, T, at the total, the biggest constraint that adds up to is a total of 21,600. Alright. Very nice. Let's keep the ball rolling. Let's keep the ball rolling. Got some good momentum here. Alright, for one shipment, trucks are loaded first and cars are loaded afterwards. Even though trucks are bulkier than cars, a shipment can consist of all trucks as long as it is within the weight limit. Alright, anywho, find the number of cars that can be shipped if the cargo already has 480 trucks. So I am telling you what T is, and I want to find the number of cars C. All right. Well, instead of a T, I'm going to do the 480, and that's going to equal again 21,600. So I plugged in one value that's given, and I can solve for the other one. Again, do that in your calculator. All right. Combine like terms, subtract it to the other side, and divide by 3.6. Okay. I'm getting C equals 5,000. All right. What about the setup for B? Well, that's 3.6 C plus 7.5, and instead of T for trucks, I'm going to do 1,500, and then that is equal to 21,600. And again, I'm not going to get repetitive because I'm trying to keep the video as short as possible. So solve for C. I ended up getting, when I did the calculator, C equals 2875. Same thing for this one. Instead of T, you're plugging in 2736, and when I solve for C, I got 300. And then, okay, so it says T trucks. Well, that's confusing because it's not a number. but treat it like you did in the other three. Everywhere you see a T, you're going to plug in T. So, okay. 3.6C plus 7.5, well, T equals 21,600. Okay, well, remember the question is find the number of cars that can be shipped in the cargo. So if I want to find the number of cars, it wants us to still solve for C like we did in the other problems. It's just this time we don't have a T value to plug in. It just essentially is asking us to get C by itself. It wants us to still know what C is. It's just we won't have an exact number because, again, we don't have any T trucks that we have. So in this case, I'm going to, since this is plus 7.5T, I'm going to subtract 7.5T. And that's going to go bye-bye. And I'm going to go 7.5T. And I can't combine like terms because this has a T and the other one does not. So I'm left with 3.6C on the left and 21,600 minus 7.5T on the right. And lastly, to get C by itself, I'm going to divide by 3.6. So I get C equals 21,600 minus 7.5T, all divided by 3.6. Very nice, very nice, very nice. All right, moving on. A lot of problems, a lot of problems. That's all right. We like math. Skip around as you need to. For a different shipment, cars are loaded first, and then trucks are loaded afterwards. So we're reversing what we did in number 2. It says write an equation you could enter into a calculator to find the number of trucks that can be shipped if the number of cars is shown. Okay, so it says write an equation you can enter into a calculator to find the number of trucks that can be shipped if we know the number of cars. It's literally asking us exactly what we did in part D, except instead of T trucks, we know we have C cars. Okay, so again, the equation is 3.6C plus 7.5T equals 21,600. But now it wants us to write an equation that can help us find the number of trucks, given that we know cars. So it's asking us to get T by itself in this equation. So I'm going to do a very similar process that I did in part D up here. I'm going to, instead of subtracting 7.5T, I'm going to subtract 3.6C to the other side, and then divide by 7.5. Again, same process over here, but solving for T instead of C. So I get T equals 21,600 minus 3.6C, all divided by 7.5. Follow the same process you did in D, but getting T by itself. Okay. Now, use your equation and a calculator to find the number of trucks that can be shipped if the cargo already has 1,000 cars, and what if it has 40 to 50 cars? So literally, all I'm doing is using the equation, and I want to know the number of trucks, all right, given that I know cars. So everywhere that I see a C in this equation, which is right here, I'm going to plug in 1,000, and then I'm going to plug in 40 to 50. All right. I'm not going to rewrite it out, but do all of this in the calculator. Okay, plugging in exactly as you see it. Do it in Desmos, whatever you want to do, and then plug in 1,000 for C. Make sure you put that number in parentheses so it knows that you're multiplying. All right, take a second, pause the video, do that. All right, when I plug in 1,000, I'm getting that T equals 2,400. And when I plug in 4,250, I'm getting that T equals 840. Double check my math, but I'm pretty sure that's right. Alright, for yet another shipment, the manufacturer is also shipping motorcycles. Yay, which weighs 0.3 tons each. Write an equation that you could enter into a calculator to find the number of motorcycles that can be shipped. M, if we know the number of cars and trucks. Alright, so going back to our original equation. We originally had that we know, well, 3.6 tons for each car, 7.5 tons for each truck. Well, now I'm adding in a new vehicle, 0.3 for every motorcycle, and my constraint is still 21,600. So just like we did in Part A and Part D in the last problem, we're going to solve this the same exact way. But now it wants us to do it in terms of N, because we know what C and T are. So it wants us to get M. Oh, won't do that. It wants us to get M by itself. Okay. So I'm not going to go through the whole process. It's the same as before. But now I'm going to subtract 3.6C and 7.5T to the other side, and then divide by 0.3, just like I did the other times. So I get that M equals 21,600 minus the 3.6C. I'm going to minus the 7.5T, none of which can combine together because it's different variables. And then I'm going to divide everything by 0.3. And that will tell me the number of motorcycles, given that I know cars and trucks. Alright? Alright, part B, it says use your equation to find the number of motorcycles, alright, that can be shipped if we know that we have 1,200 trucks and 3,000 cars. Well, just green. Just like before, I can plug in the 3,000. That's terrible. I can plug the 3,000 in for the cars, and for the T, I can plug in 1,200. Perfect. Again, type this exactly in the calculator or in Desmos like you see it, except where you see a C, plug in 3,000. Where you see a T, plug in 1,200 in parentheses. And guys, what I am getting is the motorcycles is equal to 6,000. 6,000 motorcycles. Very cool, very cool, very cool. Moving right along. Alright, one more big problem and then we'll get to the summary. Alright. It says the Department of Streets of a city has a budget of that, $1 million something dollars, almost $2 million, for resurfacing roads and hiring additional workers this year. Well, the cost of resurfacing a mile of two-lane road is estimated at $84,000. $84,000. The average starting salary of the worker in the department is $36,000 per year. So let's keep those numbers in mind. We will write an equation that represents the relationship between the miles of two-lane roads the department could resurface, we're going to call that M, and the number of new workers it could hire, P, if it spends the entire budget. Alright, here's the entire budget. So I know that it's going to equal that big number. We're going to spend all of the money. Alright, well remember, part of it is going to the roads. Alright, so the cost of resurfacing a road is estimated at $84,000. Well, M, here we go. Relationship between the miles of two-lane roads. Good. M, and okay, so M represents the miles, okay, that we're going to resurface, and remember that a single mile is $84,000. So that's $84,000 for every mile M, plus, and then also it's going to be $36,000 a year for every worker P. So that's going to be 36,000 P. equals that. Yay, there's our equation. Alright. Well, moving right along. We're going to take that equation and we're going to solve for p. And we're going to explain what the solution represents in this situation. Alright, so being able to understand what we're doing. Let's do this in, where's my cursor? Red. Okay. So if I'm solving for p and trying to get p by itself, I'm going to subtract this quantity to the other side. So I'm going to go minus 84,000 m. And when I subtract that to the other side, I'm left with 36,000 p, and I'm going to divide by 36,000. Divide everything by 36,000. Again, same steps you took in all those previous problems. So I would get that p equals 1,962,800 minus 84,000 m divided by 36,000. And if it wants us to explain it, I'm not going to write it down, but I want you to write down what I'm saying. Is that represents the number of workers, given that we know the number of miles that we are going to do. So depending on the number of miles that I do, I can figure out the number of people I can hire, given my constraint, given my budget. All right. Let's do the same thing, but now we're solving for m. Now I'm not going to rewrite this, but again, it's the same process. Okay. Instead of getting 84,000 m to the other side like we just did in the previous problem, I'm going to get 36,000 p to the other side and divide by the number in front of m. Try this on your own, but I'm getting m equals 1,962,800. Now we're minusing instead 36,000 p and dividing by that number in front of m, which was 84,000. Again, I'm not going to write it down, but I want you to. If you had to explain it, it's the same explanation as before. Given the number of P workers, so if I know the number of workers that I can plug in for P with this budget, I can determine how many miles I can resurface. So if I know the number of workers, I can determine the number of miles that I can do as well. Not bad, right? And then lastly, 3, it says the city is planning to hire 6 new workers. All right, well, we got our P value right there. That's P. And to use its entire budget. So meaning we can use these equations up above. Which equation should be used to find out how many miles a 2-lane road it could resurface? Explain the reasoning. All right, I'm given P, and I'm asked to solve for M. Which equation? A or B? This one, right? If I plug in, I can plug 6 in for P, multiply this whole thing out in the calculator, and it'll tell me M. So part A. Find the number of miles of 2-lane roads the city could resurface if it hires 6 new workers. So we determined in A that we would use, oh wait, I starred part B, but I said part A. We would use part B, sorry. Anyway, so we would use that. Now we know which equation to use. Let's actually plug in and solve. So all I'm doing is, instead of P, I'm plugging in 6, plugging that bad boy exactly in the calculator, and I'm getting 20.8. All right, we did it. We survived the video. Now comes the summary, which I have graciously gone in and went ahead and typed it out because I know y'all hate my handwriting, and that's okay. So let's summarize everything that we did real quick. I'm going to try not to write if I don't have to. All right, remember, solving for a variable is an efficient way to find out the values that meet the constraints in the situation. So solving for a particular variable like we did all lesson. Here's an example. An elevator has a capacity of 3,000 pounds and is being loaded with boxes of two sizes, small and large. Small box weighs 60 pounds, large box weighs 150 pounds. X is the small boxes, Y is the large boxes. And to represent the combination of small and large boxes, we can write it just like we've been doing. 60 pounds for every small, 150 for every Y, and my constraint is 3,000. If we have 10 large boxes already, so we know Y, how many small boxes, X, can we load onto the elevator so they can fill, so it fills at the capacity? What if there's 16 large boxes? Well, in each case, either way, we're going to substitute 10 or 16 in for Y, because that's what Y represents, large boxes, and perform acceptable moves to solve the equation. Or, like we've done the entire lesson, we can get X by itself. So here, I moved 150Y to the other side. I divide everything by 60. And we get an equation that represents the number of small boxes given that we know large boxes. And then we would plug 10 or 16 into that. Yeah, like I said, so this equation allows us to find the number of small boxes that can be loaded X by substituting any number of large boxes for Y. And now suppose we first load the elevator with small boxes, say, I don't know, 30 or 42, and we want to know how many large boxes that can be added for the elevator to reach its capacity. All right, well again, we're going to substitute the 30 or the 40, but this time in for X because it's asking us to solve for it. And just like before, if we want to make it a little bit easier, we can solve for Y by itself. Move 60X to the other side, divide by 150, and get this equation. And now that we know what the value of X is, we can find Y by plugging in the value into the right side of the equation. So, solving for a variable before substituting any known values can make it easier to test different values of one variable and see how they affect the other variable. So that's why we solve for the variable first before plugging it in, because then if we wanted to test other numbers, we could do that too. Alright. Yeah. That's it. We did it. Under 30 minutes. Very well done. Have any questions? Reach out. Let me know. We're just moving right along. Alright. I will see y'all next time. Congratulations on another math lesson. This is your boy Forbes out.